Hello everyone. Today we are here to talk about transformers. Transformers is a neural network architecture which is powering all the new developments in AI which you look at every day. DALI, ChatGPT, Stable Diffusion, and a lot of advancements in AI in recent time has been powered by this architecture called transformer. In this class, we're going to look at what is the basic architecture of a transformer, how does it work, and we're going to look at this via the source code of transformer. So hopefully you can get a great understanding of how the internal working of transformer is. And if by the end of this class you understand this meme, hopefully you would have also gained a good understanding of what transformer is. Before you start, it would be great if you have some prior knowledge about Python. Working knowledge of PyTorch is good to have, so you can be able to play around with the code better. And I'm also assuming you have some ground level understanding of what a neural network is and what a sequence to sequence and vanilla attention models are. If you are hazy about one of these topics, it would be great if you can look back at some of these and then come back to this lecture. It would lead to a better result. So first, look at where did it all started. So in 2017, a paper called Attention is All You Need came out, and which proposed the architecture of transformer. It was surprisingly not an architecture paper but a machine translation paper. As a part of the paper, they proposed this new architecture for machine translation, but as everyone discovered before, the architecture in itself was much more versatile and can be used for a lot more great tasks than just machine translation. Before the transformer architecture was proposed, people were looking at RNNs, recurring neural networks, LSTMs, GRU, and vanilla attention were always there. And with transformer coming out in 2017, a lot of NLP and now even vision and speech work has moved to these newer, bigger architectures which we call BERT, GPTs, and vision transformers. And we'll get a better understanding of how these newer, bigger model works by the end of this lecture. So to start with, first let's look at the overall architecture of a transformer model. As this is a sequence to sequence model, it follows the typical stance of a encoder and a decoder head. So there is an encoder head which takes your input, adds something which we are calling a positional encoding to this, and then passes it through what is called multi-head attention, passes through a few dense layers of neural network, and this gives you your context vector or hidden vector, which because this was a machine translation architecture and it's a generation model, it generates auto-regressively, which is you first generate the first word, then that becomes an input to the model again, and you generate the second word in the decoding phase. So whatever you generated previously again goes through the same thing, but in this case there is another multi-head attention. The first attention is with the input in itself, just like the encoder model, but the second one is the multi-head attention between the input here and the context vector which you produced, and this is called crossed attention because now the attention is between two different sources, and again it goes to a dense network and you finally have your output. So it's a very straightforward architecture in the sense of that you don't see any fancy layers or structures of that there is some other knowledge graph or a graph network which is trying to encode something. You don't see some hidden states. It seems a very straightforward network. And another quality about this network is you see there is this thing called a multi-head attention, and this seems to repeat again and again everywhere. So entire architecture seems to be just repetitions of these multi-attention head and some variation of these, and that is what is at the center, at the heart of transformers, and that is why the paper is also named as Attention is All You Need. So what we're going to do in rest of this lecture now is to start with looking at multi-head attention and understand the core of the architecture in itself. Once we have a good understanding of the what multi-head attention is, we can just start building on top of it. We can take piece by piece every module in this network, and by the end of it we would have built an entire transformer network. So let's start with multi-head attention. Before we go to multi-head attention, we'll look at something called a self-attention, which is a subset of a multi-head attention. So there's something called a self-attention, and when you do it multiple times in parallel, it becomes multi-head attention. Okay, so what is self-attention? Conceptually, it's very similar to what vanilla attention was. In vanilla attention, you used to have a query vector, a k vector, and a value vectors. Generally, these q and k were coming from either your current state, and your q and k was coming from your hidden states in your RNN models of the encoder part, and your v vector was coming from your current state, and you would take your current state, you would go back to all the hidden states and perform an attention with them to figure out what is important. This is the exact same formulation of QKV essentially, which is scaled here. But here the interesting part is the attention, instead of happening between whatever was the sequence to sequence model current state versus hidden states was, now it's happening in the sentence in itself. So for example of sequence, if you assume a sequence of, I'm looking at this lecture at NPTEL, now each token or each word in this sentence would do attention to itself, and for each token we would have a q, k and v vector, and then the typical attention mechanism can happen, and at the end of that you would get a attention score, which essentially talks about that how this one word is dependent on every other word in this token. And the idea is coming from that previously there used to be recurring neural networks where we used to feed tokens one at a time, words one at a time, and the idea was that the neural network would build on top of each word and eventually it would have all the information. What we started realizing is, though it works, eventually it starts forgetting and it does not remember anything about older sequences. So we started adding more mechanisms on top of it by the way of LSTM and GRUs, where we added hidden states, we added some forget gates and some input gates, which talked about that, okay, now we're going to build this structure in this architecture which is going to facilitate what needs to be remembered, what needs to be forgotten. And even though that was working great, eventually people discovered that even after using things like LSTM, it's very hard to capture very long sequences in just one context vector. And that is when the concept of attention came, where they started, instead of trying to say one context vector, they kept all the hidden state, and at every point of time they started going back to each hidden state and looking at, okay, what needs to be taken here. What authors of Attention is All You Need paper realize is that a lot of benefits in this entire process are coming from the process of attention itself, and their idea was we should remove everything else. We should remove this LSTM thing, we should remove this RNN thing, we should, if attention is the one which is giving the great amount of benefit, why not just build an architecture centered around attention? And instead of trying to build on token by token by token, why can't we just take the entire data once at a point and just do attention within between, and it would learn what is important for what. When I say, okay, NPTEL in a sentence, like I am watching this lecture at NPTEL, what's the dependency on NPTEL on every other word it would learn? This dependency can be anything. We are not talking about a specific dependency like co-reference resolution or what is the post tag of it. The idea being that this method is generic enough that it can figure out complex relation between tokens, and whatever needs to be learned by the model for the task it needs via the process of back propagation and end-to-end learning, it would learn whatever that relation quote unquote is. We just need to build a general mechanism which model can use for it. So once we understand it, the actual mathematical basis of implementing attention is very simple. You have your data. This data gets through a linear transformation and becomes the q vector, the k vector and v vector. So in on the screen right now you see there is a dummy attention class which I have built, which takes some data of size 50 by 50, and similarly I have generated 3 weight vectors, one for k, one for q, one for value. And now my key vector is just a linear transformation, a matrix multiplication through this. You can also imagine this to be like a linear layer, but where all your biases are 0. So it's instead of your typical wx plus b, right now we are just doing wx, and that's how it's implemented, and we'll look at how this is implemented in a more PyTorch sense. But this is a very basic NumPy implementation where so the key, query and value vector just becomes these. So what would be a typical forward pass through this? You'll take your q and k vectors, you'll do a matrix multiplication, and this would give you what we call scores, which one it would tell you, okay, this is what the potential importance of these two relations are. Now that you have that, so let's say you have your key vector coming from one token and query vector coming from other token. Matrix multiplication between them would give us scores, which is indicative of, okay, what is more important here. And then we scale these scores here by under root dk. We'll talk about this in detail later, but for now if you ignore it, then we just pass it through a softmax, which, as you know, softmax takes the input and converts it into a probability distribution of kind where everything adds up to 1 and all the values are between 0 and 1. So this then scales this matrix down and convert this into a importance score kind of thing where everything is 0 to 1. The value which is the most important is the highest. The parts of the vector which are less important are closer to 0. And now because we have this importance kind of score, we can just do a matrix multiplication with V, and the idea is whatever is more important in V would stay as much as it was originally, but whatever is not that important in V, it would be scaled down to closer to 0 values, okay, and that would eventually give us what we call the attention score. So let's just try to run this block of code. I have intentionally here commented the under root dk part to show you why the under root dk is important. So if we run this code without the under root dk, we are doing everything, but we see these very ugly not defined and infinity and minus infinity values in it. This does not look like something which is very useful as an attention score. Why is that happening? That is because when we are performing this q and k multiplication, you can eventually start having very large and very small values. This becomes a distribution. The values of the score matrix, the variance of score matrix is very large, and when that passes through softmax, if you have very small values, they turn into infinities and not defined. This is not really nice. We ideally want to end up in a very good distribution, but why is that happening? Why do you end up with such large variance? So if you think about it, Q is generally a not uniform normal matrix where the mean is 0 and variance is 1. So is K. But now when we do a matrix multiplication of Q and K, each cell in the score matrix is, you take a row in Q, you take a column in K, each elements get multiplied, and then all of them are added together is one cell in score matrix. So now when you multiply multiple two terms which are sourced from a mean 0 variance 1 distribution, what you end up with a new term which would have a mean 0 and a variance of 1. But now you have dk terms like this. So whatever was the dimension of that, in this case 50, you would have 50 different terms like this which would all be added up. So now you have 50 terms which all have a mean, which are sourced from a mean 0 and variance 1 distribution. Added all of them up together, they would still have a mean of 0, but now they would have a mean of whatever the dimension of this addition was, in this case 50, and generically what we call dk, which is the dimension of your k matrix. Okay, so now that is what is causing this variance to blow up. So now we ended up with a variance of dk. So what we want to do is, before doing anything, we want to normalize this matrix back. Your standard formula of standardization or normalization is your value x minus mean mu divided by your standard deviation sigma. Okay, so in this case we have our value which is qk. we subtract the mean, which in this case is 0, so it does not show up, and then we divide by standard deviation, which is under root of variance, because variance was d of k, we have under root dk. So what we are trying to do here is we are going to take this matrix, which we end up with the score matrix, which end up have a very big variance, and this variance can do very bad things. It can scale our values up and down, which does not work very well, especially when you are going to do this again and again. That's why after every step we normalize it all down to under root dk, and under root dk is coming from because the variance of that distribution would be dk. Okay, so now if we add this back to the code and we run this again, what you would see is now you have nice floating point numbers. Now you have nice floating point numbers, which can represent the attention score in this case. Okay, so that is what the basic self attention is. The idea is to perform the structure of attention which was already there, but instead of doing it between two different a context vector or previous hidden states and your current situation, the idea is to capture the relationships in the sequence itself, to encode them in itself. We use the mechanism of attention. And once we understand attention, which is another representation, this diagram where you get your q and k, you multiply, you scale. The optional mask step we'll talk about later, but you do a softmax and then you multiply it again with v, and this gets you what is called as scaled dot product attention. Attention because it's an attention matrix, dot product because you have done a qk dot product and then you take whatever the score is and multiply it with your v, and scaled because there has been like a scale operation here. So you see, that's how it becomes scale dot product attention. And now the idea is you take this attention and you do it multiple times in parallel. Okay, and that is what becomes multi-head. And this is another very big benefit of attention or transformer architecture over previous architectures like RNN and LSTMs. By the virtue of those being recurring networks, they were sequential networks which made the processing very slow, because a token would be processed and then the next token would come and then the next token would come. In this case, if you see, for each token you are doing with some other token qkv. Okay, and now because this calculation of attention is independent always of two tokens. So I'm watching this class on NPTEL. The calculation of NPTEL with I and watching with on are two different completely independent calculations, have nothing to do with each other. All of these can be done in parallel, and that is what gives us huge amount of efficiency gains in terms of computing time compared to our previous architectures like RNN and LSTM. And now multi-head attention is we're going to do that process multiple times in parallel. And the benefit, the intuition behind doing it in multiple times in parallel is that, okay, we talked about that attention is going to turn some one kind of relation. However, there can be multiple types of relations which are important when you are trying to understand a topic. Of course, not one kind of languages are very complex. Any kind of unstructured data is very complex, and there are multiple nonlinear relations which are present in there which can be helpful. So each head would be able to learn a different kind of relation which we want to capture, and eventually we can combine all of them together and make like a encoded version of it. Okay, so now what we do, what you see this code here, it's called multi-head attention, and now we looked at the heart of this, which is self-attention in a basic NumPy code. Moving forward in this lecture, everything else is built in a more PyTorch structure, so we can run all of it together in the end as a network. But if you look through this, pretty simple code where you start with what is the dimension of your model, what is the number of heads, and this gives you the dimension for each head. So you see this assert statement here. It's interesting to understand this. How generally the architecture of a transformer work is, you start with the dimension of embedding in the start, and till the end you have the same dimension. So let's say if you're starting your transformer with 512 dimension embeddings, the output embedding by the end of transformer for each token would also be 512. Now in the middle you have this multi-head attention, where what you're gonna do is you're gonna do attention multiple times in parallel, and then you're gonna concatenate all of them together. If you look from self attention, we started with the input of 50-50 and we ended up with the output of 50-50 also, which means the dimension during attention process does not change. So if you're starting with a 512, and let's say if you have 10 heads, then you end up with 5120 embeddings, which can be scaled down, but a different method which the transformer embedding transformer architecture people use is that each head would have the dimension which is equal to the total dimension divided by number of heads. So for example, if you want to have 10 heads and you are starting with 512, then each head would have a dimension of 51.2, and now you see the problem. Dimensions can't be 51.2, it has to be integer number. That's why a condition which transformer networks have, and was the first condition we have while initiating the model, whatever is the number of heads you choose, it should have a complete divisibility with the dimension you start with. So there are nice integer dimensions available for each head to work for. Okay, so in case of 512, you would end up probably starting with 8 heads. So 512 by 8 and 64, each of your head can have a 64 size embedding, and eventually when we take 8 embeddings of 64 size and we concatenate all of them together, we again end up with a 512. Okay, so once we match this condition, we declare these variables. We declare our q, k, v as we talked about. These are wx plus b operations, where b is essentially 0, so this is like a linear layer. So I declare 3 linear layers with no biases, and then our output layers is also finally going to be a linear layer. And then how do we do a forward pass? We take our q, k, v, and we get a q vector, k vector, v vector. We do some reshaping so we can compute multiple heads in parallel. I'm not going into specific details of how this reshaping is happening, but the idea being, you have a 512 embedding, and now you need to pass it on to your self attention header 64. Intuitive thought is that you scale down each 512 version to different 64 version and then send it out, and that's not a wrong thought, that would work, but again that is computationally expensive. And ultimately what you are doing when you are scaling it down, you are doing some form of a linear transform on these embedding to get them to 64. The authors structure it, and there has been different implementations which do it different ways. One of the methods is scaling down to 64, but this is a different method where you take your entire embedding of 512, you break it into chunks of 64, and then you multiply it with parallel QKV vectors, and the idea is that is still a linear transformation, and the model would be able to capture whatever it needs to capture. And in this case, you reduce the number of matrix multiplications you are doing, in which leads to efficiency gains. There are different methods also where instead of having 3 different QKV vectors, you can just have a 3-dimensional matrix and you can do that multiplication. These are different ways of parallelizing these operations. The implementation details are kind of optional here, because eventually to use this in your real life you would be using a library like PyTorch. However, it's the more important thing to understand here is the intuition of multi-head and how each head gets a lowered version of your initial dimension. How it's done, there are multiple ways of it. In this case, we take our initial embedding and we break it into chunks and pass it to each head, and this is what I am doing here, reshaping so I can do the projection. Once I have the projections done, I do my Q and K, I scale it by under root dk. We'll come and talk about mask later, but then once we have our attention weight, we do a softmax, and this gives us our attention output. I reshape it back to the original form which we wanted, which is your batch size, sequence length and dimensional of the model, and we pass it through a final layer and we get our output. Okay, and this is what a multi-head attention looks like. It's everything which we did here is just the thing we did here, it's scaled here, and now I instead of just taking it through one head, we break it into multiple heads and did it in parallel. Okay, now what is this mask? We talked about that in attention. We are taking each sequence and we are looking it to every other sequence. So if your sequence length is, let's say, L, you end up with the L cross L matrix where each cell would tell you what is the score of this token with this other token. However, at many a times you don't want every token to look at every other token. Okay, what are some cases like this? So a common thing which we do in neural networks, that all the sequences in the data set are not of the same length, but to standardize our input, we pad shorter sentences with padding tokens, so we have same length. Now these padding tokens are good for so it makes our computing process easy, but while doing the computation we don't want to learn any relation between the pad token and our actual tokens. So what we can do is we can just say, okay, mask these tokens, which is we're going to send a separate variable which is going to keep what token needs to be masked. Okay, and before we do a softmax, we just going to whatever the score was previously of qk, and after scaling we don't care. Before sending it to softmax, we'll replace it with like a minus infinity or a very small negative number. The reason being, when a very small number added there would pass through softmax, it would eventually become 0, which means we do not want to give any attention to this token. Another classic case where you end up using masked attention is in the decoder phase, which we'll talk in details later, but the idea being, when you are generating a sentence, you want to have a attention with everything which is produced before this token. So in the sentence of I am watching this on NPTEL, when I am on, I want to have attention with I and M, but watching is not generated yet. Because watching is not generated yet, the current token should not have any information about what is coming in future, and so we only want to look at attention with previous tokens. So we'll create this, we'll take the entire upper triangle, or we'll take entire half of our attention score and we'll mask it. So we can only look at attention in one direction, and the backward direction, and not in the forward direction. So that is what mask is doing. So whatever needs to be masked, so here I just check, okay, I just reshape the entire mask variable so it can be broadcasted with this matrix, and then wherever there is, we do a mask fills, that wherever the mask is equals to 0, just fill it with minus infinity, and this when passed through the softmax would eventually lead to zeros. Now that we have done multi-head self-attention, we are good to go. We have learned the heart of it. Now everything else is very simple. So if we go back to our initial diagram, we have learned this part. So now what is there? There is, okay, some input embedding and some positional encoding we'll talk about, but then essentially we do multi-head attention, we normalize it, and you see these residual connections. So every block has a residual connection. So it provides the standard benefits which residual connections provide, that your gradient can be passed on through this path also, so there is no vanishing gradient in longer networks and everything. So you have a residual connection, so you add and normalize, and then you pass it again to a feed forward network, which is a normal two dense layer network block, and then this again happens, and this entire process repeats n number of times, and that is what we call your encoder block. So now let's build the rest of the parts of it. And why is it happening this way? A good analogy which has been proposed over time of how to understand this: imagine the multi-head attention block, so this block, to be the communication phase of the network, where in this case model is not essentially, instead of model is, what model is doing is every token is talking to other token, and between them, and they're trying to figure out, okay, what is important, this relation is important, this relation is important, and all of that is discovered, and all of that coming from multiple heads is this concatenated together in this one vector. But now these tokens and these structures communicated between each other, and they gave us, okay, this is all what is important independently. But now all of this information which we know about what is important and what is not needs to be assimilated together and saved it into one context vector, so it can be one continuous block. And to take all that communication information and combining it together to make like one information vector is the job what this feed forward network is doing. So communication happens here, we get some great output from the communication that, okay, this seems to be important, we based on the importance we scale everything, and this is done multiple times via multiple heads, and we have small 64 dimension information, assuming the input overall input being 512, 64 dimension small vectors which has told us everything. Now we just pass it through a feed forward network which has two dense layers, and they would together learn that, okay, how to mix all of this information together to make one vector. So to implement rest of these parts, feed forward block, as I talked about, is just two linear layers. So you have a linear layer, you get the output of that linear layer, pass it through ReLU, and then pass it to another linear layer, and that becomes the output of that block. And now an encoder layer just simply becomes whatever the input you had, you have a multi-head attention block, you have a feed forward block, and then you have two normalization block, one normalization after multi-head attention and one normalization after feed forward. And a basic forward pass would be, you have your self attention, you perform your multi-head self attention, you add the residual connection back, with whatever output you had. You also add a dropout. So your attention output, you put a dropout on attention output, add it back with the original outcome. This is your residual connection, and then you normalize it. And then you pass this new output to your fully connected feed forward block, and then you do this again. You put a dropout, you do a residual connection, and then you normalize again. And this becomes outcome of what we call the encoder layer. Okay, and so now we have looked this entire square here. Now what we need to do, this process n number of times, and we need to figure out what is this positional encoding and this inputs. Okay, so let's look at that. Once we figure out these three things, once we call this n number of times and add those two things, we have what we call an encoder block. So look at the simple things. We have an embedding layer. First talk about what an embedding layer is. As we start with in any language with tokens like, I am watching this on NPTEL, as we would have seen with RNNs in every other case, neural networks can't take words as input. Words need to be encoded into vectors which can, or just numbers which can represent the information. Initially people used to do it with things like TF, IDF. Eventually with word2vec we moved to more denser vectors. Okay, and in this case also every word is encoded as a dense vector of 512 or whatever dimension your model is, as we talked about. So this is done through embedding layer. Instead of using some predefined embeddings like word2vec or something, we just start with random embeddings, and again the idea is in the training process the model would learn as an end-to-end process. So this is the embedding layer. That is very simple. So you take your entire data set, you make a vocabulary out of it, and each word in the vocabulary get assigned to a ID or a token number, and every time the model sees this token number is present, it assigns the same embedding to it. And what this embedding is in itself is learned through the entire end-to-end learning process via backpropagation. That is great. We'll come back to positional encoding, but then what you have is you take your encoder layer and you declare it n number of times. So we run a for loop and we declare n encoders layer, which we talked about, which is we want to do the whole encoding process n number of times, and eventually we put a dropout and we have our outcome. So we have our embedding layer, we do the positional encoding thing, we will talk about it, and then we do a dropout, we do this encoder layer thing n number of times for as many layers as we have, and that's finally is our encoder output. So what is this positional embedding? We talked about that how instead of previously like RNN where the token 1 went and then token 2, token 3, all of these tokens go together in this case, and every token can look at every other token and figure out what is important and what is not. Even though this leads to great efficiency gains in terms of computation, that everything can be done in parallel, the problem with doing it in such a way is we have lost the sequential information here. RNN inherently has a sequence in it where token 1 is going after token 2 is going after token 1 and then token 3 and then token 4. So it's capturing the sequence information there. Here it's more like a bag of words that these 5 words entered and look at something between them. But we want to capture the sequence information because at the end of the day that is important for these networks. So the idea is you use something called a positional encoding, which is you take another encoding, another vector which accounts for the positional information of these in the sequence, and you just add it back to the original embedding, and that is almost a hint, a signal for the model to which model can catch on easily that okay, this is the first token, this is the second token, this is the third token, okay, and this needs to be consistent across inputs, so model can just learn that okay, this signal every time just denotes what is the position. Now there can be multiple ways of doing it. Of course, any signal we want to give ideally should have some properties. It should be unique in the sense it should not be repetitive, so model can't have this signal represents position 1, then 2, and then position 3 can't be the same signal again. It needs to be a different signal, so model can decode between them. So you can't have like repeated numbers on it. So a very good example of this can be why just not use linear sequence numbers 1 2 3 4 5 6 7 8 9. That is a great idea, but that has another difficult property is when you start having longer sequences, because this is something which is added to the original embedding which you see here. If the values in itself are very big, they're gonna displace the original embeddings in the space too much, and the embedding is going to lose the original meaning it had. So we don't also want to do that. That's why we can't use something like 1 2 3 4 and just extend that ahead. So now we want something which can denote position, and it's confined in a range, so our entire space does not get jumbled up. There can be multiple functions like this. In fact, initially when transformers were starting to use, they used the initial formation which are presented by the paper, but eventually people have figured out that there can be what kind of positional embedding you use can have great effect on your outcome, and different experiments and different papers has been written on positional embeddings. You can also learn these positional embedding themselves, which also the original paper do, but their argument was that the benefits gained from that is not worth the extra compute. What we use here is the initial method which the paper proposed, but of course there has been different methods since then which you can go out and look for. But here the idea was that why not use a cosine or a sinusoidal function to be able to denote position, because they are confined in a range of 0 to 1, and they are very easy to decode by a network. The problem with them are they are repeating functions, okay. So how do you get past that? So the idea was for each position use a cos or sine function of different. So first you can use a sine function for, let's say, even positions and cos function for odd positions, and for each position use a different frequency of it. So so imagine a cos or sine wave, and how as you change the frequency the repetition cycle comes closer or farther apart. The idea is for each position use a cos or a sine wave of different frequency. These are confined waves. Model can easily differentiate them from other signals, and by using every frequency we can differentiate each position in itself, that one earlier position would have a much larger frequency than later positions, okay. But again, it's most important in this case. This is a slightly hard topic. Most important in this case to understand what is a positional encoding. It is a signal which is provided to a model, so model can know what is the sequence in the input itself. There have been multiple ways of doing it. Depending on the task, there can be multiple ways of doing it. One of the methods which are proposed by the initial paper was this. Initial paper also experimented with learning these embedding themselves, and that also works. It's just this is a much simpler method, and this also works equally well. But once you have done that, you have your entire encoder block fixed out. So let's recap what we looked at. We looked at attention, which is just qk scaled by v. Once we do this multiple number of times, we have our multi-head attention. Idea of doing it multiple number of times is that each head can capture a different kind of relation, and now each head has given us what is important in the sequence at multiple levels, and then encoder just block becomes is, we had our input, we add some sequence information, we do the multi-head attention is what is the communication phase where everything talked with everything else and figured out, okay, this seems to be the important for this token is important for this one, this relation is present here. We normalize it, and then we pass all this information to a feed forward block which would assimilate all of this together to make a nice information vector, and we do this entire process n number of times. We can build upon it. So each encoder layer, so each sequence of doing this would be able to learn more and more complex relations out of it, and eventually you would have a context vector which captures all the information of whatever initial sequence you started with, and that can be then used to perform the downstream task.